stabilized. So I'm very happy to start the last session of the day, which is an exciting session about streaming and mostly about graph streaming. And we will see a combination of interesting talks. The first one will be about the Boolean hidden matching, which is a useful lower bound technique. The second one, just remember the order. So the second one is about adversarially robust streaming, adversarially robust coloring of for graph streams. And the last three are exciting works about, so the third one obtains optimal bounds for dominating set, both for insertion only and for insertions deletions. The fourth one gets a better rounds space trade-off for the feedback arc set problem in tournaments. And the last one resolves a long line of research on a dynamic maximum matching in streams. So let us start with the first talk, and I'm happy to invite Samson to talk.
Okay, yeah. So if I properly shared my screen, you should be able to see that the talk is on noisy Boolean hidden matching in applications. This work is by Kapralov, Amulya, Musipatla, Jakab Tardos, who prepared these wonderful slides, but couldn't speak today due to the time difference, David Woodruff, and myself. Okay, yeah, so the Boolean hidden matching problem is a one-way communication problem that was first studied independently by two different works in 2006. And in this problem, there are two players, Alice and Bob, and Alice receives a binary vector of length n. And these correspond to labels on n vertices. And then Bob receives a matching on these n vertices. It doesn't have to be complete matching, but it can be. And Bob also receives an edge parity vector that we call W. And when we say an edge parity, we say that an edge has parity which is equal to the sum of the labels of the vertices. For example, the first edge on the right, which is labeled by 0, is equal to the sum of the two labels on its endpoints, which are both 1. So in this problem, Bob must decide whether the parity labels are all correct, which is the yes case, or all incorrect, which is the no case. And in this example, we have the vector of the edge parities being all correct because the one corresponds to, so the second edge corresponds to two vertices that have parity 1 when they are added together, and the bottom edge has parity 0. So all the labels are correct, and this is the yes case. So the Boolean hidden matching problem has been used to solve or to show lower bounds for a number of graph problems in the streaming model. I see that a bunch of authors of these previous works are in attendance, but just to belabor the point, it's been used to show lower bounds in triangle counting, maximum matching, max cut, and maximum cyclic subgraph, to name a few. But one weakness of this communication protocol is that it's known that Boolean hidden matching requires root n bits of communication. And so this often translates to getting lower bounds of root n. And this may not be the most satisfactory because a lot of these problems seem to be a lot harder. And indeed, if we consider the generalization to Boolean hidden hypermatching, where each edge is now a hyperedge of size t, and Bob needs to define the parities on these hyperedges as either all being correct or all being incorrect, then one can show that the Boolean hidden hypermatching problem requires communication n to the 1 minus 1 over t. So this Boolean hidden hypermatching problem has been used to show stronger lower bounds in these problems I listed before. So we'll go over one quick illustration of lower bound reduction. Actually, it's not even going to be an example. I'll just briefly describe some bits of the gadget. So in the streaming lower bound for max cut by Kapralov, Khanna, and Sudan, they reduced the problem to be HH, which is Boolean hidden hypermatching, using the following gadget. So Alice gets a number of vertices, n vertices to be exact, and Alice encodes each bit into 4 vertices. So we won't go with the rest of the details, but the point is that after the reduction is done, if the label of the edge parities is correct, then there is no odd cycle. And if the label is incorrect, then there is an odd cycle. And in both cases, the cycles will have length roughly t. So this is the case where w equals 0. So this is the correct case, and this is the incorrect case. But you can see that the red line in both these cases induces a cycle that is quite long. So Kapralov, Khanna, and Sudan show that a 1 plus epsilon approximation to max cut requires 1 n to the 1 minus epsilon space, roughly. But again, these cycles have length 1 over epsilon, roughly speaking. So these graphs can have a large diameter. So natural question is whether these hardness results still apply if the diameter of the graph is quite small. So this motivated us to study the noisy Boolean hin matching problem, where the yes case still corresponds to edge parity vectors that are all correct. But in the no case, only a small probability of flipping the edge labels will induce a small number of incorrect edge labels. So recall that in the Boolean hin matching case, all the edge labels are either all right or all wrong. But in noisy Boolean hin matching, they're either all right or a small number of them are wrong. And we observe that this is a distributional communication problem, and that we can similarly define a noisy Boolean hin hypermatching problem. So intuitively, this should be a harder problem. And indeed, I'll describe this plain text protocol that does show it could be harder. So consider the protocol where Alice just sends S bits of the labels of the vertices. Now, if Bob detects an incorrect edge label, then he can answer no, or otherwise he answers yes. And the probability that the edge parity is known to Bob is roughly S squared over n. This can be shown by saying that the probability that Bob knows a single vertex label is S over n. So, the probability that Bob knows both is S squared over n squared. And then there are n edges, so you do union bound. It's like roughly S squared over n. But now for us, the probability that Bob knows an edge parity and the corresponding label is noisy is going to be roughly p times S squared over n. So in this case, we see that space S equals root n over p suffices. And recall that p is smaller than 1, so this is going to use more space than root n. Similarly, we can show a similar protocol for noisy Boolean hin hypermatching. And it turns out that this protocol is essentially tight. Namely, we can show a randomized one-way protocol that succeeds with constant probability for this communication problem, requires root n over p bits of communication. And using this lower bound, we can get lower bounds for one-pass streaming algorithms for max cut, max matching, and maximum acyclic subgraph. And these lower bounds have, the lower bound is root n over p. But the caveat is that these graphs in these constructions can now have small diameter. Namely, they can have constant diameter. So before I talk about the analysis, I'd just like to mention the previous approach, which uses Fourier analytic approaches to bound the L2 squared distance between the posterior distributions of the edge labels in the yes and no cases. Now we can try to mimic this approach using the p noisy operator, but it turns out that the L2 squared distance is quite loose, and we can't actually show a good difference between the posterior distributions. So the natural approach using Fourier analytic techniques doesn't quite work. Or at least we don't know how to show it works. So instead, we use an information theoretic approach, and we reformulate noisy BHM as multiple instances of Boolean hin matching. Namely, we create roughly 1 over p instances of Boolean hin matching. And each of these instances are going to have random size. So they're going to have some size that's drawn from the binomial distribution with n events and probability p. And now in the no case, we'll define a single instance of BHM. So one of these 1 over p instances is going to be no, and the rest are still yes. And in the yes case, all these instances are going to be yes. So intuitively, it means that we need to solve all of these BHM instances independently and correctly. So we can do this using the complexity of a protocol based on internal information cost. And it's been previously shown Well, communication complexity of Boolean hidden matching has been shown, but one can use that to show that the information cost of Boolean hidden matching is roughly root n. And now the idea is that we have 1/p instances. Each of these instances will be of size roughly n times p due to the randomized instance. And so if we multiply these together, we'll have root np communication for each information cost for each of these instances. There are 1/p instances, so that gives the lower bound of root n/p. And now we can use a similar construction to Kapralov, Khanna, and Sudan to show that we can get 1 plus epsilon approximation lower bounds that have roughly n space for small diameter gadgets. So this problem max cut is still hard even if the graph has small diameter. Similarly, we can get lower bounds for maximum matching and maximum cyclic subgraph. So in summary, we introduced the problem, p-noisy Boolean hidden matching, and we show that it requires space communication root n/p. And then the natural generalization, Boolean hidden hypermatching requires communication n to the 1 minus 1/t divided by p to the 1/t. We use additivity of internal information cost to show this lower bound, and we get new streaming lower bounds for these graph problems, even when the diameter has small size. And that's it. Thanks.
Thank you very much, Samson. The model is we only have 10 minutes per talk, and there's not a lot of time for questions. So there's time for one quick question per talk maybe, and then 10 minutes at the end of the hour. So is there any question? Okay, if not, let's thank Samson again. And our next speaker will be Manuel Stoeckl. And he will talk about adversarially robust coloring in graph streams.
Okay, now I'm unmuted. You can hear me, right? Yep. So my name is Manuel Stoeckl. I'm going to present slides for a paper on adversarially robust coloring graph streams. This is a joint work with Amit Chakrabarti and Prantar Ghosh. Brief overview, I'm going to explain what problem we're looking at, the results we have, if time permits, simplified overviews of the proofs and algorithms, and then mention a few open problems that we're interested in. So what is adversarially robust streaming? It's a setting that's been introduced in the last 1 or 2 years. When we think of it, you have a 2-player game between an adversary who provides a stream of elements and an algorithm whose goal is to, at any point in that stream of elements, produce an output depending on what has been seen so far. As with all streaming algorithms, the algorithm is allowed limited space to remember what the stream inputs are. We say that an algorithm is adversarially robust if the algorithm produces outputs that have a low error probability of their task for any given adaptive adversary. By an adaptive adversary, I mean one which, following the game, can look at previous outputs of the algorithm and try and use those to construct an input on which the algorithm is more likely to fail. In this framework, the standard streaming model is like having an oblivious adversary that never looks at the outputs of the algorithm. And it's also worth mentioning that deterministic algorithms are automatically adversarially robust because in deterministic algorithm, you're never allowed any error. Okay. So the problem we're looking at in particular is streaming graph coloring. We're given a sequence of edges of some n-vertex graph. We're not allowed any repetitions in the edges. And the edges form a graph whose maximum degree is delta. The goal of the algorithm is to output at each point in the stream a k coloring in the graph, where k is some parameter which is at least delta plus 1. In the standard streaming setting, the sort of paper that already solves this. It's by Asadi and Khanna from 2019, and they give an oblivious delta plus 1 coloring algorithm, which uses roughly n bits of space. However, like all existing coloring algorithms, adaptive adversaries can break it. The question we're looking at in this paper and talk is whether there exist robust streaming algorithms require significantly more space to solve this problem. So we find that the answer is yes. In particular, if we have any adversarially robust k coloring streaming algorithm, then it needs at least n delta squared over k bits of space, where delta is the maximum graph degree. As a consequence, if we want to delta plus 1 color or O delta color a graph, we're going to need omega n delta bits of space. Similarly, if we're allowed only semi-streaming space, so ON space, then we need at least delta squared colors. There's also I should mention a work independent to ours, which finds that if you're allowed ON space, then a deterministic algorithm needs to use even more than delta squared colors. They need to use some quantity which is exponential in delta, in fact. We also find, we also find adversarially robust algorithms which can delta squared color an edge insertion stream, and which can delta squared color an edge insertion stream using roughly ON squared delta space. This algorithm has a few variations which work for graph streams where you're allowed to delete edges that you insert in the past. And we also provide a delta cube coloring algorithm that uses semi-streaming space, but with the trade-off of needing access to a large pool of random bits. So the core of our lower bound is to reduce to a communication problem, which we call subset avoidance problem. This is parameters T, A, and B. The idea is that you have two players, Alice. One of the players knows a subset U of size A and wants to send a message to Bob. Bob, on the other hand, wants to use that message to discover a given, discover a set V of size B, which is entirely disjoint from U. You can solve this problem by sending a set. You can solve this problem by sending the set U entirely, but that's can be fairly inefficient. A more efficient approach for this is to pick a random for Alice to pick a random set V and send only the intersection of U and V. We prove that this problem needs at least omega AB over T bits of communication to solve with constant error. So how do we link this to the graph coloring problem? It turns out that if we're given an adversarially robust sketch for graph coloring, we can find it's possible to find many edges that are not in the graph encoded by the sketch. Specifically, if you take the given a sketch for a graph, you can find the if that's for the graph, you can produce a coloring of the graph, and then you can find non-edge, and you can find many non-edges, since between every pair of edges with the same color, since between every pair of vertices that have the same color in your coloring, there cannot be an edge in the original graph. Furthermore, because the sketch is adversarially robust, it is possible to use some of the non-edges that were revealed by the coloring. Take those non-edges, add them back into the sketch. So now you have to add them back into the sketch to compute the coloring of your updated graph, and that coloring is going to reveal even more edges which are not in your original graph. So because of this, the sketch is very similar to a void. In fact, you can use this graph coloring sketch as part of a protocol which solves multiple copies of a void. The exact details of how we're solving multiple copies are a bit finicky. You can see them in the full version of the paper. And then now that we have that reduction, the lower bound on the message size for a void can show implies the desired lower bound on the size of sketches for graph coloring. Okay, looks like I'll need to speed up to keep this talk in bounds. So to briefly describe one of the upper bound algorithms, for a delta squared algorithm, we're using a variation on existing technique in the sketch switching, where at different times we are using sketch switching, where the algorithm stores multiple copies of an existing sketch, and at different times it switches between which sketch it is using to compute its output from. This algorithm we're using in this algorithm, we also maintain a buffer of recent edges. And by using that buffer, we can delay how often we need to switch between the underlying sketches for our coloring. The trade-off is that we end up using more colors than a few more colors than in the oblivious case. We also present a delta cube coloring algorithm. Again, I can only give a short description, but this is modifying the core of some existing streaming graph coloring algorithms. These algorithms typically assign a random palette of colors for every single vertex, and use random palette of colors for every single vertex, and then only store edges, and only end up storing edges for which conflicts between end up storing edges for which palettes between different vertices overlap. And then when you color vertices using color filling palettes, you only need to check those few edges that you've stored. The main trick here is that you use a different set of colors. The main trick here is that for every single degree of a vertex, you use a different subset of colors, and that makes it possible to prevent the adversary from predicting what palettes are going to be used for a vertex when you after you add an edge to it. Okay. So conclusions: we prove a lower bound on we prove an omega n delta squared over k lower bound for robust algorithms. Space lower bound for robust algorithms to k color an edge insertion stream with maximum degree delta. We also present a few robust coloring algorithms. Open problems that we found interesting. One of the main ones is whether or not the lower bound that we've proven is tight. For example, with semi-streaming space, the lower bound we have predicts that you need at least delta squared colors. However, the best that we proved as of time of writing was O delta cube colors. We've since improved that slightly, but there still is a gap. We're also interested in knowing whether there exist robust coloring algorithms for very long streams that have many edge insertions and deletions. And like much of the rest of the field, we'd like to find a space separation between oblivious and adversarial models for natural estimation problems, like the example of approximating second moment of return cell streams that's been studied a few times over the last few years. Okay, thank you for listening.
Thank you very much. So I think our time is up for questions on this one, but again, there's time for question in the end of the hour. So please stay if you have questions then. And thanks Manuel again. Our next talk will be by Christian Konrad about optimal bounds for streaming dominating set.
All right, all right, good. I hope you can see the screen. All right, so this is about dominating set in graph streams. It's a joint work with Sanjeev Khanna from University of Pennsylvania. So we talk about, so this work is about the data streaming setting, and so the streaming setting is sort of characterized by this typical sequential access. Now, we look at graph problems. So in graph problems, we have two main models that we work with. There's the insertion only model, where essentially edges arrive one by one in arbitrary order. And we look at an insertion deletion model where edges arrive, but can also be deleted again afterwards from the stream. And yeah, in both settings, space little o of n squared would be what we would be aiming for, because this would essentially be already a non-trivial bound for very dense graphs. Now, so this work is about dominating sets. So here's an example. We've got an input graph G. Then let's first look at what a dominating set is. So a dominating set is a subset of vertices such that the inclusive neighborhood of this subset is the entire input graph, so all the vertices. So in other words, for every vertex that's not included in the dominating set, there must be a vertex in the dominating set in its neighborhood. A minimum dominating set is one simply then of smallest size, and we're interested in approximation algorithms. So a dominating set is an alpha approximation if its size is at most alpha times the optimal size. So the approximation factors here are larger than 1. Now, the dominating set problem as such has not been studied in the data streaming setting so far, but a related problem, the set cover problem, has been studied quite extensively in the data streaming setting. So let's talk therefore first a bit about set cover. So in set cover, the setting is quite similar but different. So the input is that we have a universe of size n. Then we've got a set family of sets. So overall, we've got m sets, and these are all subsets of our universe. The output should be a smallest subset possible of these sets that cover the entire universe. So we need to find a small subset, again, that covers essentially the entire universe. Now, we all know that these two problems, you can reduce them to each other in linear time, but it turns out in the data streaming setting, they're somewhat different. And but before we talk about this difference, so there's an important connection in this direction in that if we had a dominating set instance and like this one, we have some input graph G, to obtain a set cover instance, we can just see that if we set the universe to be the set of vertices of our input graph, and the set family would then consist of the inclusive neighborhoods of the vertices that we've got. So we would have essentially an instance on n sets and a universe also of size n here. So if we want to solve dominating set using a set cover algorithm, for example. Now, going to the streaming model. So set cover has been studied quite extensively in the streaming setting, and the model that is considered is typically here a set arrival setting. So that is, the arrival order is, we see the sets of the input one by one in arbitrary order. So we have some sequence of the sets, but then what does that mean, the sequence of the sets? It means that you learn about the identifier of the set and as well about the elements that are contained in the set. So in other words, whenever a set arrives, you know exactly what the set looks like. Right, so this is the perhaps best described as a set arrival setting. And the following results are known in a one-pass setting in the streaming setting. So interestingly, for an approximation factor of root n roughly, we can get a semi-streaming algorithm with space basically O tilde of n. Now, if we want an approximation factor that's better than root n for approximation factor little o of root n, then suddenly the space kind of explodes and you need space n times m over alpha. So there's some phase transition going on at this approximation trade of root n. For anything better than root n, suddenly the space is n times m over alpha, but for root n, space n is enough. Good. So, so we know pretty well what is happening for set cover in the set arrival setting in the streaming setting. Now, if we go to a dominating set now, then it's of course much more natural to consider an edge arrival model because ultimately dominating set is a graph problem and we say edges arriving one by one. So if we see edges arriving one by one, then we still can connect sort of this setting to a set cover setting. And for example, if the edge 4, 5 arrives that connects vertex 4 to 5, then we could sort of on the fly construct a set cover instance indicating sort of an edge arrival set cover setting, indicating that the set number 4 contains the item number 5 and the set number 5 at the same time contains the item number 4. So we can sort of relate these problems still to each other. However, we don't have anymore the property that entire sets arrive. We'd rather have an edge arrival setting where sort of a set arrives with sort of one element that belongs to it. And ultimately, it means that over the course of processing the stream, the elements that are contained in a set, they might appear at arbitrary moments in the stream. And that will be ultimately the difficulty that we have to deal with. So in a sense, streaming dominating set can be sort of compared to an edge arrival set cover setting where we have essentially n sets. Good. So now, the results that are known for set cover in the set arrival setting, interestingly, there are two results that apply as well for the edge arrival setting and will also translate to dominating set. And let's see, that's in fact this result here. So as long as if we want an approximation factor better than root n, then the upper bound and the lower bound of this result, they translate to dominating set. That is space essentially n square, because we have n sets now for dominating set. N square over alpha is best possible for approximation factors little o root n. So this even holds in insertion deletion streams. So the setting is essentially already ruled out by this result here. But still, there are some open questions. Of course, then the main question is what happens at exactly this threshold root n, where we see this phase transition for set cover. So it is not clear that the algorithm for sort of set arrival set cover would translate to an edge arrival setting. So the question is there as well a phase transition here or not? And yeah, the question is as well, what happens in the insertion deletion setting if our approximation factor is not little o root n, it's and is an omega of root n. So the results that we get are as follows. So first we have an algorithm for the insertion only setting. And indeed, it turns out similar to the set arrival setting, there's as well a one-pass algorithm for dominating set with an approximation factor of roughly root n and semi-streaming space. So this algorithm can also be applied to arbitrary set cover instances that have this edge arrival in the edge arrival setting. And yeah, we see, in fact, exactly the same phase transition here as well. Now, there's not enough time really to go into the algorithm, but as an intuition, the reason the set arrival situation works so well is because entire sets arrive one by one, and you can essentially with each arriving set decide whether this set should be included in the solution. You can do that if the set covers enough new vertices in the input graph. So that's sort of the big advantage. Now we can't do this here anymore. So instead, what we do in terms of strategy is to say, well, ideally we want to include only vertices in the solution and dominating set if they have a large enough degree. So we'll just let the first root n edges go. That means the sort of vertex accumulated a decent amount, a decent degree. And only then we attempt to insert this vertex when it has accumulated a root n degree into our solution. But of course, we can't do this for all the vertices. So we essentially downsample. We include with a probability of 1 over root n here. And we carry on in such a way. And this inclusion probability would be exponentially increased step by step. And this indeed effectively works to not take too many vertices, but you still take the vertices of large degree and you end up with a similar approximation factor. Then we have a lower bound as well for the insertion deletion setting. So this lower bound says that this situation in insertion deletion streams is in fact quite simple. So for an alpha approximation, there's a lower bound of n square over alpha in the insertion deletion setting. And now this holds for any value of alpha. So there's a matching upper bound that translates from the set cover setting. So this setting is essentially ruled out. Now this lower bound is an information complexity lower bound with a direct sum argument using a set intersection problem that was defined in the paper cited down here. So as a summary, essentially, we have optimal bounds for dominating set, both in the insertion only and in the insertion deletion setting for essentially the whole range of parameters, approximation parameters alpha. Again, the upper bound extends to general set cover instances with space m plus n, if you have m sets in a universe of size n. And a follow-up work recently, we could prove that this space is essentially also optimal in the edge arrival setting. So we need this dependency on m and n as well for a root n approximation. There's maybe one open question here, and that's that essentially almost all set cover and dominating set now space lower bounds that have been streaming, they require that algorithms produce a cover certificate sort of indicating a specific vertex is covered by, this vertex in the solution. And they really strongly rely on this assumption. And the question is really whether we can avoid this. All right, then, yeah, thanks very much for listening.
Thank you, Christian. Again, we're a bit over time, so we'll keep the questions for the end of the hour. But thanks, Christian. And we will move to our fourth talk of the session about semi-streaming feedback arg set. here's so I'm happy to have Anubhav Baweja from CMU.
Hi, am I audible? Okay, sounds good. Hi, my name is Anubhav, and today I'll be presenting an efficient semi-streaming PTAS for the toolman feedback arc set problem done in few passes. This was done in collaboration with Justin Gia and David Woodruff at CMU. So we'll start off by first defining the permutation, the cost of a permutation pi on a vertex set V and a weight matrix W, where the weight matrix W can be thought of as the adjacency matrix on a vertex set V. And it is essentially the number of back edges that are present in that particular permutation. And the goal of the feedback arc set problem is to find such a permutation pi star, which minimizes this total cost, which minimizes the total number of back edges in that permutation for any permutation. And on tournament graphs, this problem is much more easier to manage because even though on general graphs, this problem is NP hard, and it was shown by Mellon that even on tournament graphs, this problem is NP hard. There already does exist a PTAS for this problem on tournament graphs, and therefore our goal is to produce a streaming algorithm which achieves the same approximation factor. So there are like several motivations and applications for the tournament feedback arc set problem. The most prominent one being Kimeni-Young rank aggregation, in which we can kind of rephrase the tournament feedback arc set problem to be thought of as a ranking by pairwise comparison problem, where we are given a list of items and we are given pairwise preferences between all pairs of items, and we want to find an ordering of the items which has like the least amount of disagreements. And this has like a various application in search engine results and machine translations. Previous work on this problem is vast. So I guess the most straightforward thing is that sorting by wins, which is just like sorting the vertices by their in degree, already gives us like a 5 approximation factor. And this algorithm is polynomial in n, only requires one pass, and requires like only n log n space. And throughout this presentation, we will be using this O star notation, which basically means that we'll be hiding, which hides away polylog over epsilon factors. Recently, in a SWOTA paper by Chakrabarti et al., they presented a couple of algorithms, including the modified K-Wick sort, which can achieve a 3 approximation factor and can also achieve this like a very nice trade-off between passes and space of like P passes versus O star of n to the 1 plus 1 over P space. PTAS, as we mentioned earlier, does exist. The Chakrabarti paper also presented 1 plus epsilon approximation factor algorithm, which has a 1 pass and O star of n space. So it seems like the ideal solution, but unfortunately it uses exponential in n time. And then finally, our result, which achieves a 1 plus epsilon approximation factor in a polynomial time with P passes and the like O star of n plus 1 over 1 n plus n to the 1 plus 1 over P space, as was similar to the trade-off that the Chakrabarti paper achieved. Yeah, so as we mentioned earlier, that this is our result, and this is what we will be striving towards in this presentation. So in order to first present the algorithm, we first need to understand this idea of a single vertex move, which is essentially a local optimization method, which was used in a query efficient setting by Alon, and also in the PTAS presented by Kinnan and Shruti. And the idea behind a single vertex move is all you do is you take a vertex and you move it to a certain different position in the permutation, such that the overall cost of the permutation decreases and you get a better permutation. The idea of several of these algorithms is to apply repeatedly cost improving single vertex moves to somehow reach a local optimum, and show that local optimum in fact does give us a 1 plus epsilon approximation of the minimum feedback part set on the tournament graph. So the key insights of our algorithm in order to actually emulate it in a streaming setting are that we first want to approximate the cost improvement achieved by these single vertex moves using sampling. We can't store the entire graph, we can't store everything because we are trying to achieve subquadratic space, and therefore we cannot always have access to how much cost improvement we will achieve by making a single vertex move, and therefore that has to be done with sampling. Another key insight is that we want to have multiple copies of these sample sets, because once we use a sample set to make a single vertex move, we now have a new permutation, and in some way we want a fresh sample set that is still independent of the permutation and still has all the desirable properties that we needed to have. A third and key insight we had was that we only need to make strong single vertex moves, which essentially means that we only need to make moves which are long. By long, I mean they are linear in length with respect to the subproblem, and they also achieve a significant cost improvement, which means that they have up to polylog and over epsilon factors, a linear amount of cost improvement as compared to the length of the move itself, and therefore the actual size of the subproblem. Another insight that we made was that we can make multiple single vertex moves in parallel, such that the realized cost improvement is still good. So if we have a set of cost improving single vertex moves which have their own cost improvement, we can actually make them at the same time. And approximate their costs using the same sample sets, in such a way that the total cost improvement that we would have anticipated from making all of these single vertex moves individually is approximately the same as the realized cost improvement when we made all of them in parallel. So we start with the algorithm overview. We first obtain a 5 approximation by sorting by in degree using the Coppersmith result. And then we recursively, first of all, if the input is small enough, we brute force it. If the cost is high enough, we want to use an add approximation algorithm that was given by Fries et al. And we show that algorithm can also be simulated in our semi-streaming setting. But otherwise, we want to call this approx local improve method, which is the key local optimization method, which actually makes the single vertex moves on each subproblem in this recursive algorithm. And then finally, once we make those local optimizations through approx local improve, we divide the problem into 2 subproblems and then further recurse down the tree. Now, this is the meat of the algorithm. Approx local improve, the local optimization algorithm. The sample sets of EVI are used to approximate the cost improvement of the single vertex moves. And then this method essentially executes strong single vertex moves in parallel until no strong single vertex move actually remains on that particular permutation. So in order to get a high level idea of why this algorithm works, we need to break down the cost of a permutation into 2 parts according to our algorithm. So one is can be considered alpha x, which is the total, where x is a leaf in the recursion tree, and alpha x is the cost incurred by that particular leaf. Whereas beta x is the cost incurred at the internal nodes of the recursion tree. The total cost of this particular permutation is just the sum of all the alpha x and all the beta x's. And this is an important lemma that we got from Alon in his query efficient setting work, where he shows that the expected value of the total sum of all the cost at the internal nodes, as well as the optimal cost at the leaves, is at most 1 plus epsilon times the optimal cost on the entire permutation. So this is like a very important for us, because ultimately at the leaves, we always end up either brute forcing or calling the add approximation algorithm. And therefore, we do achieve a very close to the optimal solution at the leaves. And therefore, all we need to do is we want to achieve, we want to show that we make every strong single vertex move that Alon's algorithm makes, that we are making as well, in order to actually be able to use this lemma.
Our time is officially up, so maybe take 1 or 2 minutes to wrap up.
Okay, yeah, I'm almost done. Okay, sorry. Given all these suppositions and the fact that we're only making strong single vertex moves, we show that the total that because every single strong single vertex moves has a cost from linear in n, and the maximum cost of a feedback arc set can be like theta n squared, the number of times new strong single vertex moves will be created by making these strong single vertex moves is very small. And therefore, the number of sample sets that we need to store, and therefore the number of passes we need to make, is also very small. And therefore, we are able to get away with executing this algorithm in the semi-streaming setting. We can also see that the proxlocal improve method only requires 1 pass. So the entire algorithm only requires log n passes with high probability, 1 for each layer of the recursion tree. And finally, we can partition different layers of the recursion tree based on the sizes of the subproblem to achieve a trade-off in p passes and O star of n to the 1 plus 1 over p space. And finally, other than the feedback arc set result, we also achieve a few minor results, such as a deterministic algorithm for finding strongly connected components in tournament graphs, and some single pass lower bounds for some directed graph problems, and also some multiple pass lower bounds for strong connectivity in few passes. And that is it. Thank you.
Thank you very much, Anubhav. We'll go straight to the last talk of this session by Vihan Shah from Rutgers.
Hi, so can you see my screen?
Yes.
Okay, and the cursor as well, right? Okay. So yeah, hey everyone. So today I'll be talking about an asymptotically optimal algorithm for maximum matching in dynamic streams. This is joint work with Sepehr at Rutgers University. So what is the matching problem, right? So you're given a graph, and a matching is just a bunch of edges that don't share any endpoints. And the maximum matching is the matching of the largest size. So here you can see a matching, and here M star is the maximum matching of this graph. The setting we're interested in is streaming. And in this setting, the information comes bit by bit. In a stream, you observe the current bit and update the memory. And once this bit goes ahead, you don't have access to it anymore. So in terms of graphs, the edges of the graph will appear in a stream, and the vertices are fixed from 1 to n. And since we're looking at dynamic streams, the edges can be inserted or deleted. So let's look at a quick example. And edges are being inserted in this graph. And this red edge here shows an edge deletion. And this is the final graph. So in this setting, we want to output a solution at the end of the stream. So it's important to note that you don't have to maintain one throughout. And the goal is to minimize the amount of memory used. Unfortunately, there's a lower bound here. So you need n square bits for this problem. And also you can trivially store the whole input in n square bits. So there's no non-trivial solution. And when such things happen, you usually look for approximation. So the question is, what about an alpha approximation? You want to return a matching M with size at least M star over alpha, where M star is the maximum matching. Can we get to flow of n square space? So what is the trade-off between alpha and the space. So previous work tries and answers this problem. Konrad 15 gave an upper bound of n square over alpha square and a lower bound of n 1.5 over alpha 4. Asadi et al. Gave an upper bound of n square over alpha cube. This tilde over here is hiding polylog factors. And a lower bound of roughly n square over alpha cube. Chitnis et al. Gave the same bound. And then Dark Konrad 20 gave a lower bound of n square over alpha cube bits. And now you see that the gap between the best known upper bound and lower bound is polylog n bits, right? So this is the best known upper bound and the lower bound. And these polylog n gaps occur very frequently in dynamic streaming literature. And usually the reason is this main technique for finding edges, which is L0 sampling. So the problem is in a dynamic stream, you want to find just one edge of the graph. And that itself is a non-trivial problem because what if you find an edge and that's deleted later? So L0 samplers are a key tool to solve this problem. And they can basically sample edges uniformly at random from sets of pairs of vertices that undergo edge insertions and deletions. They can be implemented in log cube and bits of space, but they also need log cube and bits of space. And many problems, they have this polylog overhead because of L0 samplers. Connectivity, for example, has this lower bound of n log cube n by Nelson U19. So we raise the question, is this polylog always necessary, right? So now we show a result. So we prove asymptotically optimal bounds on the space approximation trade-off. So we give a dynamic streaming algorithm that with high probability gives you an alpha approximation, and it uses n square over alpha cube bits of space. So this closes the gap up to constant factors, right? Because Dark Konrad had a lower bound of n square over alpha cube. And we also answered the question that we raised in the previous slide that we always don't need this polylog overhead. So we don't have it here. And you might be wondering why alpha less than n to the 1/2. It's because for greater alpha, there's not enough space to output the answer. So n over alpha is greater than our space bound. Okay, so now we'll show how we prove these results, starting with a few assumptions. So the input graph is bipartite. The maximum matching has a large size of omega n, and getting a theta alpha approximation is enough. And it's important to note that all of these assumptions can be lifted. So what is the approach we use? So there are two steps. The first one is called match or sparsify. So it either gives you a large matching or it identifies a hard instance. And the second step is to solve this hard instance. And now we run both of these algorithms in parallel. It's important to note that. Okay, so let's look at match or sparsify. Over here, we either get a large matching, which is of size n over alpha. So this is the matching, and we call it MEZ. And also it's important to note that we run in n square over alpha cube bits, right? Good. So we either find this large matching and we're done. If this matching we find does not have a large size, so this thing over here, if it has size less than n over alpha, then if you look at the subgraph induced on the unmatched vertices, this green portion here, it has only O tilde and edges, and it also has a very large matching. So this is our hard instance, right? The idea for match or sparsify is basically you sample n square over alpha cube polylog n random edges. This polylog n is in the denominator, and you do the sampling using L0 samplers. So you see that the space will be n square over alpha cube bits. And then out of all the sampled edges, MEZ is just a greedy matching over all the sampled edges. And then we come up with a property that is similar to the residual property of greedy matchings. And it's different enough, but it's along the same lines. So now we're left with this hard instance, right? So this is what we have to solve. And match or sparsify gives us this partition at the end of the stream. So it's important to note it's at the end. In particular, you get this matching MEZ, right? And this will be important. It will be important for us to remember what MEZ is. So I'll just keep this diagram on the bottom here. So this is our input graph. The first step is to partition the vertices. You partition it randomly into groups of size alpha. Now, if you look at one group, what you do is you look at all the groups on the right and you sample 1 over alpha fraction of the groups and you call it its neighborhood. And this is done to reduce the number of neighbors of VI. So now there are omega n over alpha pairs of groups with exactly one edge between them. We can prove such a thing, right? So the picture kind of looks like this. So there's VI, VJ, and there is exactly one edge between them. And Vi and Vj, they do not contain any vertices of MEZ, right? So they don't contain any vertices from here. So now, if we are able to recover all such edges, we get a matching of size n over alpha, omega n over alpha, and we're done. Okay, so our goal will be now to recover all such edges between Vi and Vj. So now, if you look at Vi, it completely lies within this green portion here, right? Because it does not contain vertices of MEZ. And now the number of neighbors of Vi are n over alpha squared, right? Because most of its neighbors here, and we did a subsampling of 1 over alpha, so this becomes n over alpha squared. So how do we get this edge? We can trivially just store all the edges of Vi, right? That'll give us n over alpha squared times log n bits of space. Okay, that's easy, but we don't want this log n factor here. We want n over alpha squared bits. And it's important to see why, because n over alpha groups will then imply a space of n square over alpha cube. The log n factor would have messed up our space bound. So now if you see that Vj also does not contain any vertices of MEZ. So Vj also lies within here. So now you can just recover n of Vi minus MEZ. You don't have to recover all of n of Vi. And this is exactly what our sketch does. So we come up with a sketch called sparse neighborhood recovery. What does it do? So you're given Vi at the beginning of the stream, and you're given MEZ, this matching, at the end of the stream. Sorry. And you want to recover n of Vi minus MEZ, this moon-shaped region here. So our sketch does it in n over alpha squared bits. And now you can see that all the neighbors of Vi that are within Vj, they lie within this region here, right? Because Vj does not contain any vertices from here. So now we're able to get this endpoint of Vj, but we haven't recovered the edge completely yet. We know this endpoint, but we don't know this one. Okay, so what do we do for that? We store neighborhood sketches for both Vi and Vj. So now if you look at the neighborhood sketch of Vi, it will tell you, oh, there is this vertex u within Vj, which is its neighbor. And now you look at the neighborhood sketch of Vj. It'll tell you that, oh, within Vi, there is this vertex v, which is its neighbor. And now since you get both of these conditions, you know that uv is the edge you're looking for. And you've recovered that edge. And thus you're done, right? You can recover a matching of size omega n over alpha. Now we conclude. So we give a dynamic streaming algorithm that with high probability gives you an alpha approximation, and it takes n square over alpha cube bits of space. The lower bound of dark Konrad 20 is n square over alpha cube bits, and this makes our algorithm optimal. And these polylog overheads are not always necessary, like in our case, right? But these polylog overheads are very frequent. So the question we raise is, can our techniques be used to bypass these polylog overheads? And some problems to think about is like vertex cover, dominating set, vertex connectivity. So this is all I have. And thank you so much for listening.
Thank you, Vihan, for the very nice talk, and thank you to all of the speakers. These are very nice and impressive results that we've seen in the last hour. And I think now we can have some time for questions. So you can ask questions to any of the authors or any of the speakers or any subset of the speakers. And since we are the last session, so we are free to go over time, I guess. So if anyone has since the attendees that are not panelists technically cannot show themselves and ask questions, so you can either write in the chat or in the QA that you would want to ask a question, or just to ask the question in the QA in the Q&A. So let me maybe start with a question to Manuel, if you are here.
Yes.
So maybe it might relate to something that you said in your talk, but so your result with the delta cube, the upper bound with the delta cube, the colors. As far as I remember, it uses sketch switching, which is kind of a primitive technique in adversarially robust streaming. And I wonder whether maybe differential privacy related techniques can do better, or what, or maybe you can tell us a bit about the improved bound.
I mean, we haven't really thought about differential privacy for in conjunction with sketch switching that well. One of the reasons we've avoided it seems to be that, well, first off, it's not really clear how to apply differential privacy for coloring to begin with. And second, in general, colorings reveal a lot of random bits at once. So, yeah.
Thanks. Okay, there's a question by Sepehr to Christian. Can you see it, or should I?
Yeah, that's all right. That's all right. So yeah, this question is about the multipass setting for set cover and dominating set. So there are multipass algorithms for set cover that work in the set arrival setting that essentially have in p passes a dependency that's roughly n, and I think it's rather n to the 1 + 1 over p roughly. And indeed, this works out. So you can get similar algorithms also for the edge arrival setting. So you get exactly the same dependency, and it should be met by the existing lower bound on the multipass in the multipass setting by Amit and by Amit's paper.
So since it's technologically a bit challenging, take the time to write in the chat if you have questions, or we can promote you. Meanwhile, one question also to Christian about dominating sets. Do the approximation bounds become better if, for example, we have a guarantee about some upper bound on the dominating on the size of the dominating set? I mean, so that is scaled with the parameter.
The interesting thing is, I think the worst case seems to be indeed when the dominating set size is constant. So the lower bounds all assume a dominating set size of 3, or perhaps even sometimes of size 2. And so this doesn't help. I think you can indeed do the opposite. If you knew that the dominating set or set cover is large, in fact, the optimal set cover is large, then your space dependency can actually become slightly better, but not the way around. So it's sort of the opposite, I guess, what you would expect in that sense.
Thank you. Okay, so there's another question in the Q&A. And this is another question to Christian. And this is about whether you consider the problem in random order streams and whether the approximation factor can be improved there.
So that's a really good question. We looked at this not necessarily for dominating sets. I'm not entirely sure whether you can improve for dominating set, but if you look at the generalization and you look at the sort of edge arrival set cover setting, and you look at random order, then indeed we can and have already obtained a slightly improved bound. There was this, in my talk I mentioned that we obtain a lower bound saying space omega of m, the number of sets is necessary for achieving a root n approximation in adversarial order. And it seems that this lower bound can be broken. In fact, in the random order setting, you get little o of m space for root n approximation for that. So indeed, is a very good question. And the problem seems to behave differently in the random order setting. Again, maybe another thing to add is that in dominating set, we essentially have n sets in the universe of size n. In set cover, we have m sets in the universe of size n. And in a sense, we have a trivial lower bound of omega of n in general if we wanted to sort of store a cover certificate to say which sort of element of the universe is covered by which set. Now, we also get a trivial lower bound in the set cover setting of omega of n, even though we have m sets. Now, this is a bit sort of the setting is a bit different because in set cover and dominating set, because we have this different number of sets. So the n in the dominating set corresponds to both the number of sets and the universe size, and in set cover it doesn't. So looking at it from a set cover perspective is in a sense, we get more insight into the problem because these parameters are separated. And sort of there's the dependency on the sets and on the universe size. And yeah, so I think studying the problem from the set cover perspective is more interesting, in fact, or it provides more insight into it.
So the next question is to Anubhav by Sepehr. And this is whether there is evidence that there is no semi-streaming algorithm for 1 to epsilon approximation in polynomial time for just a single pass. So your result is in few passes. The question is about a single pass, the same result in a single pass.
Yeah, I'm not aware if there's any lower bound like that. But also, I guess, is this question for Tuneman graphs or just like for feedback arc set in general? And I guess like for either of them, like I don't know if there's like if there exists a lower bound like that. Yeah, for Tuneman graphs, I'm not aware if there's a lower bound like that.
I also have a question to Anubhav. What you showed is, I mean, you basically use the local improvement step of Elon, and I wonder whether these local improvement steps also take a major role in non-streaming algorithms.
Yeah, I think so. I think in the context of like Alon's original paper, like they used it in a query efficient setting, and even in the original PTAS, like that's like not a streaming algorithm, and that also uses these single vertex moves. So I think in general, in like a lot of literature of the feedback arc set problem, like say, single vertex moves are kind of like used in very different kinds of settings.
Thank you. Okay, we'll wait maybe 1 more minute for if there are questions, and if not, I guess we can end the session. So, okay, so there doesn't seem to be. I don't see any questions until now. So, so thanks again to all the speakers for this and very nice results and very nice talks, and see you tomorrow. So good evening, good night to everyone, depending on, or maybe good day for those.
Bye, thank you.
Bye.
Thanks, Omri.
Bye.